Thank you. Thanks very much for having me. It's great to be here. After spending some time on the other end of the lake, it's very nice to explore Kingston. I walked by the lake this morning. It's very beautiful. So I understand this is a fairly broad audience, so I want to encourage people to ask questions if you get lost so that everyone can stay involved throughout the talk. If I don't finish all the material, that's totally fine. So today I'm very excited to tell you a kind of extended research program that I've been working on, which is using astrophysical black holes and gravitational waves to look for new ultralight particles beyond the standard model, including my favorite beyond the standard model particle, just called the axion. So first, just for some motivation, as a particle physicist, I'm interested in finding out answers to different puzzles that we have currently in our particle beyond the particle model of the standard model. So what we know today, which one's the light? Oh, here. What we know today encompasses a few orders of magnitude in energy from, for example, the electron to the top quark. And of course, we also have lighter particles and massless particles at these lower energies. And most of the frontiers that are being explored is going to higher energies through colliders such as the LHC, or looking for very weakly coupled particles that may be the dark matter of the universe. And a lot of experiments are going to weaker couplings and sometimes lighter masses. That's a regime that's being explored. But most of the effort today is going on in this kind of energy range, and that's very important because there are things like the hierarchy problem or the dark matter problem that have pointed us to these scales. But those are not the only problems that we have in the standard model. In particular, we want to explain the Planck scale. Why is gravity so much weaker than other forces? We want to explain neutrino masses. Again, dark matter doesn't come necessarily with a particular scale. The dark energy problem. So I want to motivate going to different scales other than what is shown here. And in particular, there's one problem which is called the strong CP problem, which is quite theoretical. And I'll try to have a cartoon description of it, but please ask questions. So basically, the statement is that in the standard model, you expect order 1 CP violation in the QCD potential. What does this mean? CP violation is a violation of charge symmetry, so plus or minus charges being exchanged, and parity symmetry. And in the particles that talk to QCD, like quarks and gluons, and we see that these quarks and gluons don't obey these symmetries in other interactions that they have. But if you restrict the sector to just talking to each other and not talking to, say, the weak bosons, then we find that there's no violation. So somehow it's completely undone in the strong sector. And people realized in the 60s, I think, maybe the 70s, that this would, if there were this type of violation of these two kind of fundamental symmetries, the neutron that we have, it would have what's called an electric dipole moment. So in a background electric field, it would look like the neutron has a small charge separation. So this is a picture of a neutron, and there's a d is a dipole moment, and mu is a spin of a neutron. So the kind of classical cartoon picture, which I took inspiration from some notes by Anson Hook, is saying, okay, let's take a neutron as a ball of quarks. It has 2 down quarks and an up quark. If you were given this problem, just place the quarks randomly inside the neutron in your E&M class and told to calculate the dipole moment, what you do is you take the charge of each particle and the vector to the position of each particle, you sum over the 3 of them, and that gives you the total dipole moment, right? That's the charge separation multiplied by the charges. And you say, oh, okay, the neutron is about 10 to the minus 13 centimeters in size. The charges are all 1/3 or 2/3 of the electron charge. So you get, for an angle theta, as drawn here, you get that the dipole moment of the neutron is about 10 to the minus 13 e-centimeters. So that's the cartoon picture that you would calculate. If you do it in full quantum field theory calculation, it turns out there's an extra suppression because the neutron overall is neutral, so you have to couple the photons through a loop. So instead of 10 to the minus 13 e-centimeters, your prediction would be 2 times 10 to the minus 16 e-centimeters, where this angle theta is somehow characterizing how randomly these quarks are placed inside the neutron. Now, if we go out and do the experimental measurement, you see the response of the neutron in an electric field. You find that instead of 10 to the minus 13 or 10 to the minus 16, what you get is 10 to the minus 26 e-centimeters, and that's just an upper bound. So far it hasn't been measured. So that means that if you were in charge of very carefully placing these quarks inside the neutron, you'd have to line them up so that the angle between them is less than 10 to the minus 10. And that's what we call the strong CP problem, is that even though in the standard model we expect this angle to be a parameter of order 1, so far experimentally we see that it's a number that's very, very small. And so this has been known for a long time, and what was realized by Peche and Quinn is that you can solve this problem quite elegantly by saying, well, if this angle is just a random parameter in the theory, there's no reason why it should be so small. It should be order 1. But if this angle corresponds to some energy, for example, in a CO2 molecule, there's some energy associated with the bonds between the oxygen and the carbon. And so if you have a potential for what this angle should be, naturally the angle will minimize the potential energy. For example, if I try to bend the carbon, that will cost some energy, so naturally the carbon will relax to this configuration where all of the atoms are lined up. So if you do something similar, but for the neutron, you can call this theta parameter instead a particle called the axion, whose potential exactly corresponds to how big this deviation from symmetry is. And so if this axion is a background field or is a field in our universe, it will tend to make this angle relax to a very small value. So that is might be a bit abstract, but what you get out of it is a new particle which talks to these quarks and gluons. It solves the strong CP problem that I mentioned. It was also realized that it's a great dark matter candidate, and it comes out with of many other theoretical models. For example, theories that try to unify the standard model with gravity. But that aside, it has a very simple parameter space, and this is, if you want to take away one point from this more theoretical discussion, the axion has a mass that's determined by how it talks to these quarks and gluons. And so the mass, it can be very, very light, 10 to the minus 6 eV or even lighter. And so remember, before I was talking about the standard model was down here, but here we have the axion can start being as light as an eV and going down to all the way to 10 to the minus 12 eV. And it has a one-to-one, the mass has a one-to-one relationship with how weakly it interacts with other particles, both itself and particles in the standard model, parameterized by this scale FA. So the lighter the axion becomes, the higher this FA scale, and the more suppressed its interactions are with the particles around it. So that makes it very difficult to look for because it's very light and very weakly interacting. And in particular, I'm going to be focusing on this part of the parameter space where there's currently not many ideas for how to go after this particle in the lab. So you can see here, this is from the PDG review from a few years back. We have ideas of how to look for the axion in supernova. There's some constraints now in an experiment called ADMX, which is a very impressive laboratory experiment that looks for axion dark matter, but as the axion gets lighter and lighter, its interactions get weaker and weaker and becomes increasingly hard to look for. And so that kind of motivates trying to extend the reach of beyond the standard model searches to scales that are very large and to particles that are very light. So just in the usual sense where particles become lighter and lighter, their typical size, their Compton wavelength or their de Broglie wavelength will become larger and larger, and I'll be talking about kind of macroscopic scales. So it's axions that have a wavelength of kilometers or even thousands of kilometers. So that is a bit different from typical, say, dark matter scales. Okay, so that's the plan. First, to set the stage, I'll talk about this phenomena of black hole superradiance that was mentioned, which is going to let us look for these very light particles. And what superradiance is a way to extract energy and angular momentum from rotating black holes and place it in a cloud of, in a large cloud of axion particles or other light bosonic particles in the vicinity of the black hole, and form something that we like to call a gravitational atom. And then this gravitational atom in the sky will have different signatures that you can observe today. So you'll have some gravitational signatures. As I mentioned, the superradiance extracts angular momentum from the black hole. So as the black hole spins down, we can infer the presence or absence of such particles based on measuring black hole spins. And the very large amounts of axions around the black hole will be able to source gravitational waves that you can see at experiments such as advanced LIGO that's operating today. And then if I have time, at the end, I'll mention some recent work on what happens when we include axion self-interactions. Because there's a very large density of them nearby the black hole, they can start interacting with each other and sourcing axion radiation that can then be detected in the lab. Okay, any questions so far? Okay. So as I mentioned, I'll be talking about very light particles. And why am I even talking about black holes in the first place? Just to give you a bit of intuition why this could be interesting, let's look at black holes in our universe that we've observed so far. First of all, they're a huge source of energy that you can possibly extract to use for your search. But also they set a typical length scale. So if you calculate the size of a black hole, say the 30 solar mass black holes that LIGO saw emerging in 2015, the horizon size of these black holes is about 100 kilometers. And if you convert that 100 kilometers into a length scale, into a Compton wavelength, this is about the same size as a 10 to the minus 12 electron volt particle. And that's exactly the kind of masses that we're interested in looking at in terms of the QCD axion. These are masses that are hard to look for and well motivated in terms of what scales we expect to find this particle. So before I get into the black holes, I just want to do a kinematic example of superradiance because it's a process that's not very well known. If you start with basically what superradiance is extracting energy from a rotating object. So let's start with a cylinder. If you have the cylinder and it has some friction-full surface around it, scatter a ball from the cylinder as such. Then if the friction is large enough, the ball will stop because it loses energy as it scrapes by the top of the cylinder. But now let's start the cylinder rotating. If it rotates fast enough, as the ball passes by, the top of the cylinder is actually moving fast compared to where the ball is hitting it, so it can actually give the ball a kick. And the ball can extract energy from the cylinder, which is somewhat counterintuitive because usually when you have friction, you expect energy loss. Here instead, the ball gains energy at the expense of slowing down the rotation of the cylinder. So that's a kinematic example of superradiance, and it's completely general. So here I give an example with a ball, but you can have the same thing happening with wave scattering in the presence of some absorption and rotation. So if instead of the ball I had a light wave scattering, it would undergo amplification. And what was realized, actually this kind of started the story for black holes as thermodynamic objects, but if you have a wave scattering off of a rotating black hole, exactly the same thing goes through. So the black hole typically will absorb the wave if it's just sitting there and not rotating. But if the black hole is rotating and the angular velocity of its horizon is fast compared to the angular velocity of the light wave, actually the light wave will gain energy and get amplified as the black hole slows down by a tiny amount. So if you shoot in a little light pulse past the black hole, it'll get amplified as it passes by if the black hole is spinning. And the condition for this happening is this superradiance condition, which is that what I just said, the angular velocity of the wave, omega A, is slower than the angular velocity of the horizon of the black hole. And in case you're not convinced, here's a numerical simulation by Will East, who's a faculty at Perimeter. So this is gravitational waves scattering from a rotating black hole. So here's the horizon surface here, and you'll see this blue gravitational wave coming in, and it gets rescattered with a larger amplitude. So the outgoing wave is red, so you can see it's much larger as it goes out, scattering from the black hole. So this is fully capturing this effect of somewhat spinning down the black hole and turning some of that energy into this larger amplitude of the gravitational wave that then leaves the black hole. So that's all well and good, but usually you're not shooting gravitational waves at black holes. That's not a very, it's not a very controlled experiment. The first step toward a slightly more controlled experiment, although still very much a thought experiment, was taken by Press and Tucholsky, which was saying, okay, usually the black hole will amplify the wave by a small amount, say a few percent, or in the case of a gravitational wave, some tens of percent. But black hole is very large and has a lot of angular momentum, so it doesn't have a big impact on the black hole. But what you can do is you can surround the black hole by a mirror, and then the light will scatter off of the black hole, grow in amplitude, and then get reflected back, grow in amplitude again, and so on. And this process becomes exponential because photons or gravitational waves are bosons. So the larger the amplitude is in the wave, the larger the probability to add more photons to the same state. And so all of these, so the amplitude of the radiation inside this mirror with a spinning black hole in the middle will grow over time, and eventually there will be so much radiation density inside the mirror that the mirror will explode. And so this was called the black hole bomb by these guys. Of course, still not very practical, probably not the best weapon to have in your arsenal, but it gives you an idea of what you need to make this process be important, which is that you need some way to keep the particles around the black hole to continue the process over and over. And one way to do that is, instead of constructing this perfect mirror around the black hole, which is not very practical, is just giving the particles a mass. That's a way to keep the particles bound to the black hole. Just normal gravitational potential, G Newton times the mass of the black hole times mu, which is the mass of, say, the axion over r. That'll keep these particles in bound orbits in the vicinity of the black hole. And if these bound orbits have the right angular velocities, in particular angular velocities that are slow compared to the black hole angular velocity, they'll get amplified by the superradiance process. So what we want for this to be efficient is that the particle is trapped close to the black hole, so this potential is quite tight, but not inside. So this gives that the scale, the mass scale that you want, which sets the scale of how this potential turns on, is of order the black hole size. So that's why these astrophysical black holes, which are kilometers in scale, are useful for looking for these kilometer wavelength particles.
That's good.
Yes, please.
So this doesn't work for bound photon orbits.
That's correct. Yes, so bound photon orbits are very unstable. So you need it to be a massive particle. Yeah, that's a great question. Yes?
Is there any reason you pick a black hole and not another compact object like the neutron stars?
Yes, so the black holes are probably some of the simplest, at least theoretically, objects that we know. So we know exactly how this calculation goes. And I'll talk a little bit, I'll comment more on that later. Basically for black holes, they're much more efficient at producing these particles. So there have been people that have studied what happens around rotating neutron stars, for example. That's also a good thing to explore. Typically, those are make a lot more assumptions about what's inside the neutron star, and the rates are not as good, but yeah, it's also an interesting direction. But yeah, ask me again later if I don't fully answer your question. Another question? No? Okay, good. So we have this gravitational potential between the black hole and these particles. So to give a bit of intuition of how this works, let's compare it to something you all know, which is the hydrogen atom. So the hydrogen atom is a proton and electron bound by electromagnetism, and the coupling here is alpha E and M, which is 1/137, and that's what goes in the 1/r potential in hydrogen. Here we have a gravitational atom. By analogy, we define a new gravitational alpha, which is the coefficient of the 1/r potential, which is g Newton times the mass of the black hole times the mass of the particle. Or alternatively, it's the ratio of the black hole size to the particle Compton wavelength. And similarly, you have the typical size of these axion clouds around black holes, which are the Bohr radius in a hydrogen atom is n² over alpha me. So that's the Bohr radius. Here we have the cloud radius, which again is n², where n is characterizing the principal number of the level over alpha, the gravitational alpha times the mass of the axion. And for the parameters that we'll be interested in, this is few to a few hundred black hole radii. Yes?
Does alpha also determine V over C for the axions?
Yes.
And what is that?
So typical values of alpha that we'll be interested in are between 10 to the minus 2 and 0.3. So they're kind of relativistic. And that's actually important because most of the analytic work that we've done is an expansion in small alpha parameters. So because the relativistic corrections and corrections to this 1/r potential are all coming in at higher orders. Yeah, great. So now coming to the differences between the hydrogen atom and the gravitational atom, one very important difference is that electrons are fermions, so you only get one electron per level, whereas axions are bosons, and so we can build up a huge occupation number of these particles in the vicinity of the black hole. And where exactly this number comes from, I'll get to in a second, but this is what's going to make some of these systems observable. The other important difference is the boundary conditions. So when you solve for the hydrogen atom wave functions in your quantum mechanics class, you impose that they fall off at infinity and are regular at the origin. But here we have a absorbing black hole at the origin. It's very much not regular. So what you want to impose instead is that the wave function is ingoing at the horizon. And so that introduces some non-hermeticity to the problem. You have this absorption term. So now instead of the energy levels always being real, say the mass of the electron minus the binding energy, here we also have the mass of the axion minus the binding energy, but then you have a small imaginary component that comes from this absorption at the horizon. And the sign of this imaginary term is exactly dependent on the superradiance condition. So if the black hole is not spinning, then this will be an absorption. Whereas if the black hole is spinning faster than the angular velocity of the particles in the cloud, then this term will be positive and you'll get an exponential growth of the number of particles. And here I'm using the usual language of hydrogen atoms, where N, L, M are the principal and angular quantum numbers characterizing the orbitals of the particles around the black hole. Okay, so that's the setup. These are what these gravitational atoms might look like. These are just your familiar S, P, and D orbitals. So this would be the energy density of axions around the black hole. We also thought about what happens if instead of axions, these are particles called dark photons, which are like our photon, but with a mass. In that case, just like in a hydrogen atom, in addition to the angular orbital momentum, you have a spin of the particle. So here, this is like a little polarization vector for this photon, and it can rotate around. So the black hole axis is pointing up. So this dark photon, for example, its polarization vector will rotate around the black hole. And that gives it just different qualitative features in terms of its angular momentum, because it can have large angular momentum without having a new orbital angular momentum, because the spin is going around. Okay, so what does this mean in practice? Let's take a black hole. Black hole, let's say it's born with a large spin and a mass of 40 solar masses. What do I mean by spin here? It's just the angular momentum of the black hole appropriately normalized, where 0 means short-chilled black hole, and 1 is an extremal curve where the horizon is rotating at the speed of light. So if it's born very quickly rotating, like after an explosion or supernova, you start it here in this spin mass diagram. And the blue regions are the ones that can superradiate. That is, it's spinning faster than the angular momentum of the axion that I've picked here to be 6 × 10⁻13 eV. And these are levels 1, 2, and 3, orbital angular levels. So if you have such a particle in the theory, in 10 years, any background axions around the black hole, including quantum fluctuations, will get amplified up and populate this huge cloud that looks like a 2p orbital and extract kind of a fraction of 30% of angular momentum of the black hole because of the superradiance process. At this point, this line is where the angular velocity of the black hole is equal to the angular velocity of the particles in the cloud. And so the superradiance process will stop, because it's only effective when the black hole is spinning fast enough. And here we can calculate how many particles are in the cloud. The number of particles in the cloud is exactly given by the angular momentum that the black hole lost in units of h bar. Each of these particles is in an angular momentum 1 state and carries 1 unit of h bar, and the black hole has about this many h bars of angular momentum to give. So that's where I was getting the 10 to the 75, 10 to the 80 number before. Now at this point, the first level stops growing, but then you can start the next level that's localized further out from the black hole. This one has a smaller overlap with the horizon, and it's less effective at extracting the energy. But you can still spin down the black hole in about 10 to the 6 years in this case. And in the meantime, the innermost level will actually be annihilating away to gravitational wave radiation, which can be observed in observatories like LIGO. And then finally, here, the black hole is no longer affected by superradiance, because the time scales to grow the next cloud are becoming much longer than the age of the black hole or even the age of the universe. In the presence of a new BSM particle that's 6 × 10⁻13 eV. So any questions on how this works?
Is there any effect, like if just material surrounding, if there's material surrounding the black hole, is there any effect due to frictions or collisions?
Yeah, that's a great question. Yeah, there's typically black holes are surrounded by accretion disks and so on. The particles that we're discussing here, for example, these axions are, as I mentioned, the lighter they get, the more weakly interacting they get. So this axion interacts about as strongly as gravity. So the main effect of an accretion disk will be just the gravitational effect of the accretion disk, which is important to check and take into account its effect on this cloud of axions. But because the total mass in the accretion disk is small compared to the mass of the black hole and spread out over a large volume, it turns out to not matter. If you turn up the interactions of this with matter, then you can start worrying about what happens. Yeah, it's a good question. Yeah.
So in terms of mass, so we have 10 to the 77 particles. That worked out to be roughly.
Good. Yes. So it can be up to a couple of % of the black hole mass. So it takes order 1 of the spin of the black hole, but since you take that angular momentum and localize it to a larger radius, the mass that you get is smaller. And actually, I think on this plot we took into account how the mass decreases, but it's hard to see because it's so small. So the black hole is actually also losing a tiny bit of mass and moving to the left. Exactly. Yes. Maybe we should have exaggerated it for effect. Yeah. That's also a good question. Okay. And just to give you a sense, if you have particles with spin like a dark photon, as I mentioned, it can sit in a kind of s orbital next to the black hole, which has no angular momentum, no orbital angular momentum, and extract spin much faster than the axions because it's interacting more with the black hole horizon. So it can make the same path in parameter space for the black hole much faster. So in 2 days and 1,000 years instead of 10 years and 10 to the 6 years. And it can also spin down the black hole to lower values. So the dark photon will be in pink compared to the axions in blue. Okay, so that's the setup of how you build these clouds. And now let's see how we can look for them. As we just discussed, this is the same parameter space. So you have the black hole spin and mass. Here's a different particle mass, 10 to the minus 11 electron volts. And these are the same kinds of regions from superradiance that I've superimposed. But now there are also data points here, which are spin and mass measurements of black holes from X-ray binaries. Question?
Yeah, sorry. When you give a mass, are you talking about the rest mass? I mean, if these particles are relativistic, you have to distinguish.
Yes, this mass is the rest mass of the particle, and I think as the question was asked previously, these are non-relativistic in the cloud. So typically there is a correction, but it's a fractional correction. Yeah. So these are measurements of real black holes that are in binaries with a star, and then we can observe their properties and infer the spin and mass of the black hole. And if we put them on this plot, we see that some of them are well within the superradiance regions, which are the regions where you would have expected these black holes to have spun down by creating these clouds of particles around them. So since we observe these rapidly spinning black holes, we can exclude the existence of such a particle. And this is how you measure the spins of the black holes, is usually by looking at the properties of the accretion disk. So in the interest of time, I'm not going to go into detail, but I'm happy to talk about it more if you have questions. But by looking at these black holes, there are 5 of them, like Cygnus X1, which is the first black hole that was confirmed to be a black hole, as well as a few other ones. And each one gives an exclusion range on a range of particle masses. At the low end, the superradiance time is too slow to spin down the black hole in a reasonable amount of time. At the high end, the superradiance condition is no longer satisfied for these heavy axion masses. So the combinations of these measurements is disfavoring the range of axion masses between 2 times 10 to minus 11 and 6 times 10 to minus 13, approximately EV, assuming that the axion is very weakly interacting. So this FA scale is close to M Planck.
There's a question here.
Yes.
Do the initial conditions matter at all? The initial little axion cloud that you start to spin up?
Right. No. So there's the initial condition of the axion. If there are many axions in the vicinity that have a large overlap with these kinds of bound state levels, then you can speed up the process by a little bit. But since the growth of the number of axions in the cloud is exponential and you get this huge energy density at the end, any realistic initial condition is not going to matter. But it's a very important point that you don't need to rely on a background density, because even the 1/2 h bar omega of energy density that you get from quantum fluctuations is enough to seed this process.
So even if these guys don't talk to the standard model at all.
Exactly. Exactly. So that's the really cool thing about this, is that it's just a gravitational, it's purely gravitational effect. All you need is that the particle is a boson. In this case, it's a spin 0 boson. In this case, it's a spin 1 boson. And it has a mass in this range. By definition, the mass talks to gravity, and you get this effect. So it doesn't need to be the dark matter or talk to the standard model at all. So in this way, you can get a constraint on a range of masses, which is very difficult to probe in other ways. Okay, so that's what you can do with astrophysical measurements of black holes. There's a new player in town, which is LIGO. And LIGO is not great at measuring black hole spins. That's not what it's most precise at doing. But it's already seen at least 10 black hole mergers, so it has the power of statistics. So we can make the same plot with all of these black holes that LIGO can expect to see merging as it's running over the next 10 years or so. And in the presence of an axion of a particular mass, as the black holes are coming together, they're also creating these axion clouds, and you don't expect to see any rapidly spinning black holes merging at LIGO. All of the ones that start up here at high spin will move down to these superradiance condition lines. So, and similarly for the dark photon. I'm sorry, I don't know, the resolution is not the best here, but yeah. So by looking at mass and spin distributions of the black holes that LIGO can see merging, you can also either get evidence for or against having light particles in this mass range. And since LIGO is typically seeing heavier black holes than we've seen previously, you can push to lighter axion masses. So remember, the Compton wavelength of the axion corresponds to the size of the black hole for the most efficient superradiance rate. So if you have bigger black holes, you can look for longer wavelength axions, which means lighter axions. So this is the story with spin. The thing that is very exciting to me in particular is that with spins, you're mostly going to be setting constraints. If you see highly rotating black holes, you can say there's likely not a particle of a particular mass. But you can also look at gravitational wave signals coming from these huge densities of particles around the black hole. And you can think of it, again, in analogy to the hydrogen atom. If you have axions in a higher energy level and a lower energy level at the same time, just like an electron in an atom can transition and emit photons, you can have axions in an atom transition from an excited to a ground state, but in this case, in the gravitationally coupled system, you get gravitons out. And so these you can detect in a gravitational wave experiment. In addition, less in analogy to a hydrogen atom, you can get annihilations. So axions are their own antiparticles. So you can have two axions come together and emit a graviton. And you conserve both energy and momentum because you're in the background potential of a black hole. So you get some momentum from the binding energy to the black hole itself. The interesting thing is that these signals are not like the ones that LIGO has already observed. They're not these short bursts that you get from violent merger. They're very long, sinusoidal, coherent gravitational waves that last for a long time and are exactly, for example, for annihilations at the energy of twice the particle mass minus the binding energy. Yes?
Is it possible for them to annihilate into photons and with that affect the superradiance?
Yeah. So it turns out that there's no annihilation to photons. So for axions, there's no two axion photon vertex. Axions are not charged, so there's no such interaction. It is possible for axions to decay to photons. You can have one axion going to two photons. But those rates are extremely slow. Here you have kind of two powers of the axion energy density that are sourcing the gravitational wave. If you're decaying, then you just have one power of the axion energy density that enters And if you calculate for the parameters that I've picked here, you get about 1 axion from the entire cloud decaying to photons in the lifetime of the universe, so it's not a big issue. But again, if you start to play with parameters, you really crank up the photon coupling, maybe you can start seeing some other effects. Yes?
The signals of that length, like would it interfere with a LISA or pulsar timing array signals?
Yeah, good. So I'll show you some rates on the next slide. These signals fall into a frequency band that's at LIGO for astrophysical black holes. There's analogous signals that can happen if you have very light particles around supermassive black holes, and those can be looked at in LISA. And that would be probably, you'd have some monochromatic signals, but if you see over large enough volume, they could add up and start interfering with each other. And you'd need a different technique to look for it. At LIGO, each signal will stand out as kind of a single frequency line in the detector. And the signals are very long, but they're not very strong. So the typical size, the typical radius out to which you can see these signals is sort of megaparsecs, or like the local group, or maybe a bit further out for some of the parameters. But you're not going to get signals that are, say, from the early universe that are redshifting or anything like that. So you're mostly getting local black holes that are sourcing these signals. So this is what these signals look like. Again, this is a full GR simulation by Will. So here is a cloud of these, in this case, dark photons sitting around the black hole. You'll see it's kind of rotating. So there's an overall energy density here that has a time-varying component, and that source is gravitational wave radiation. And these are circles of gravitational waves going out to infinity. So just a warning, this is very hypnotizing. So this is getting everyone very excited about signatures of gravitational waves from axions. As you can see, this cloud is orbiting around and oscillating very quickly, and that is sourcing gravitational waves that then we're able to detect. So this is going back to what you can actually see if you calculate, make some assumptions about distributions of black holes, say in our galaxy, how many of them have a certain mass and spin. You can see as many as thousands or tens of thousands of detectable sources as a function of what the axion mass is. So here the gray region is the one that's disfavored by X-ray binaries, these spin measurements, and then you have, you can see many events in the LIGO band. So this is already taking into account the sensitivity of the advanced LIGO detector. And there are currently being, so this is our estimate of what you can do. In the future, there are currently analyses ongoing by groups in the LIGO collaboration and associated with the LIGO collaboration that are looking for these signals in the LIGO data. So we're very excited to see what they come up with. Was there a question?
So I'm guessing the energy lost in gravitational waves doesn't really affect the superradiance?
Yeah, so it turns out that it's a numerical question. So basically, the rate of emission to gravitational waves is parametrically slower than the superradiance growth. So what happens is you can think of it as a kind of a two-step process. First, the cloud grows, and then it slowly annihilates to gravitational wave radiation. And then the next cloud with different angular momentum grows, and then that annihilates away. Yeah. OK, so this is the kinds of things you can expect. In the final time I have, I'd like to tell you about what happens when you introduce interactions of axions. So some of you have been asking about what happens of axions interacting with the environment, with the accretion disk. It turns out that the axions also interact with themselves. Typically, in addition to the mass, they have this quartic self-interaction potential, which means that if you have many axions, a large energy density in axions, they tend to attract one another. So what kinds of self-interactions can we expect? So far we've focused on the gravitational picture. So this is the parameter space of axions is a function of mass and coupling, which also tells you about the self-coupling. And we focused on this region here, where this coupling is basically gravitational scale. If you calculate, for example, for the QCD axion, which is this line that I described before that solves the strong CP problem, what is the self-interaction, the typical quartic coupling that you associate with these particles? It's the mass squared over this FA scale squared, which is 10 to the minus 81. So you say, okay, that's silly. We're never going to see any of these self-interactions. But as I said, there's many, many particles, and the self-interaction is enhanced by the energy density. So let's try to see if you can get any effects from introducing this coupling, because from the theoretical models of axions, you do expect it to be there. So what kinds of effects can you get? One is, as I said, this coupling is attractive. So if you start with a cloud of a particular size, and then say someone just turns up the self-interaction, what happens is that the cloud will kind of shrink in radius, because you'll get an extra attractive potential. So you have, typically you have the gravitational binding energy, alpha over r, that I described, which is proportional to the number of particles in the cloud. Then you have these angular orbital energy, which is kind of a repulsive potential. And then when you add a self-interaction, you also get an extra force that's proportional to the number of particles squared over the size of the cloud cubed. So if you keep turning up either the self-interaction or the number of particles, you expect the cloud, the kind of equilibrium size of the cloud, to shrink and shrink until it collapses under its own attractive self-interaction. So that is something that may occur. Another thing that can happen is that the quartic coupling can introduce new axion levels. So previously we said, oh, you have an axion level that grows because it extracts energy from the black hole. But now we have self-interactions which can kind of circulate energy between one level of axions in this gravitational atom and another level. And I'll go through that in a little bit more detail. But if you have multiple levels that are populated, you can have gravitational transitions that I mentioned. And you can also have axion waves that are sourced from the cloud. So you start with a large amount of axions around the black hole. In addition to sourcing gravitational waves, you'll also get kind of moderately relativistic axion waves that are traveling away from the black hole, and we may be able to see on Earth. So how does this work? Let's go back to this picture of axion mass and coupling. Here's the QCD axion line. If you have very little self-interactions, so you're all the way at the bottom of this diagram, what happens is, so here I'm drawing the fractional number of axions in the cloud as a function of as a fraction of the biggest possible number you can get as a function of time in years. So here you get the blue level, the first level that grows, growing in 10 to the 5 years, which is its typical superradiance time, and then it kind of sticks around for a long time, and eventually it'll annihilate into gravitational waves. So that's the picture that I already described. As you increase the self-interaction, what happens is you can get scatterings of axions into different levels mediated by the self-interaction. So you can take two axions in a state with angular momentum 1, so like the hydrogenic 2-1-1 level, and add their angular momentum and get an axion has angular momentum 2. Typically, the superradiance rate for these axions will be much, much slower, so you may not get this level forming as you didn't in the previous slide. But because of this self-interaction, you can use the first level that builds up as a source to grow the next level. And so in this case, this can start to happen at late times. So you grow the first level, and then eventually this process of this level for sourcing the next level will grow level 2, the orange level, at very late times. Does this picture of sourcing the next level through self-interactions make sense? Any questions? Okay, so that's basically the first step that gets affected. As you turn up the self-interaction more, this level grows sooner and sooner. So here you start growing the second level almost right after you grow the first level, because the self-interactions are quite efficient. If you turn them up even more, then actually the self-interactions start competing with superradiance. So remember, before, annihilations were happening after the cloud grew completely. But here, the self-interactions can become so fast that as the first level is growing, it's immediately dumping its energy into the next level. So you cap the number of axions that you get in the first level and put them into the second level. So here you don't grow all the way to the maximum occupation number. And finally, as you keep cranking up the self-interaction, you're changing the superradiance process into a more kind of long-term extraction of the black hole. Before you exponentially grow the number of particles and the black hole spins down right away, where here you grow the number of particles to some level, but then they're slowly sitting around the black hole and slowly extracting its spin as they're annihilating both to gravitational waves and to axion waves. If the self-interaction is strong enough, so I keep turning up the self-interaction, so 0.5 here. So this purple region is where the self-interaction is so strong that you don't have, that you cap the population level of axions in both levels 1 and 2, and you never spin down the black hole, in this case, in the lifetime of the universe. So the spin constraints that I showed you before are relying on the fact that the axion is not too strongly interacting, so it lives somewhere down here. If you turn up the self-interactions enough, the black hole will never spin down in a reasonable amount of time. This is showing it again for the black hole spin. So this is the spin of the black hole as a function of time for each of these points in parameter space. So the first picture I showed you was the black hole is sitting there, then the cloud grows, and the black hole spins down very quickly. It spins down in kind of the last few e-folds of the cloud growing, where it extracts order 1 of its angular momentum. As you increase the self-interaction, the black hole still spins down at about the same time, but eventually you start limiting the axions that are around, and they're less efficient at extracting the black hole spin. So the black hole spin is decreasing more slowly over time, and eventually basically doesn't decrease at all. So this is how self-interactions can affect the picture. And the same story holds at different mass black holes, but I won't go into that. And also, because you're limiting the size of the cloud and you're introducing these extra levels, you get 2 different effects. First, the annihilations that I showed you before, the number of events that you hope to see at LIGO, eventually will decrease if the self-interactions become more strong. So this is the gravitational picture, or the QCD axion that I described to you before. But as you increase the self-interactions, you go to fewer and fewer gravitational wave events, because the number of axions in the cloud is smaller, so it's harder to see these annihilation events. At the same time, you gain new signals, because now you can have axions in 2 levels at the same time. So by definition, one level is sourcing, level 1 is sourcing level 2, so they'll be co-occupied. And you can get axions from, say, this level transitioning to axions in a different level and emitting gravitational waves. And so here, this is the green lines here are the transition signals that you might expect to see. Right now we think, this is still work in progress, but right now we think the most promising ways to look for these transitions will not be LIGO. They'll be the lower frequency detectors, like you mentioned, LISA, or maybe some intermediate types of detectors that are currently being developed, like atom interferometry detectors called MAGIS and MEGA. And these are sitting kind of in the intermediate range between LISA and LIGO. The reason is the annihilation signals are at twice the energy of the axion mass. So they have a set frequency. The transitions, just like in an atom, are kind of a fine structure energy difference. So it'll be the difference between an excited state and a ground state, which is by definition less energy than the total rest mass of the axion. So that moves the signals to lower frequency, and maybe you need to rely on different types of detectors to look for them. And then finally, as I mentioned, all of these axion clouds will also source axion waves, which will produce a flux of axions in the vicinity of the Earth, even if it didn't exist before. For example, there are experiments out there that are looking for axion dark matter, and perhaps you could repurpose those experiments to instead look for these axion waves that are coming from black holes in our galaxy. The search will be slightly different because the properties of the signal are different, but in principle you would want to use the same kinds of setups that look for these axions talking to standard model particles. So that's something that's very exciting to keep in mind for future experiments that can look for these very light mass axions as another target for these dark matter searches. Okay, thank you. Any questions on the self-interactions? That was a more technical discussion, but that's something that I find very interesting because it's one of the few ways I know to source axions in our galaxy if they don't already exist. So just to conclude. First, I hope I convinced you that black holes are a very interesting way to look for these extra light particles. We already have spin measurements that exclude previously open parameter space. And there's ongoing continuous wave searches at LIGO that can look for these types of particles around black holes in our galaxy. And so LIGO could become a particle detector. And in addition, you can have new types of both gravitational waves and scalar waves that are sourced when you have these particles start interacting with each other in the cloud. So thanks very much.